This is the Design Experts 11 front window. So now File, Edit, View, Display Options, Design Tools, Help. But nothing will be highlighted now. First I will go with File, New Design. So this is my new design. So in the previous cases, the generalized one is the regular two-level design that we have seen yesterday. Then multi-level categorical, then optimal, miscellaneous. In the miscellaneous, we have Taguchi's optimization array. Those who want to perform Taguchi's optimization can use this thing. But we are interested now in response surface. So response surface, we have central composite, box Bunsen, optimal, and other things. So first of all, I start with box Bunsen and I will finish with central composite design. So box Bunsen, the minimum number of numerical factors that is associated with this box Bunsen design is 3 to 21. Is 3 to 21. And the categorical parameters is 0 to 10. The categorical parameters are nothing but material A, material B, material C. Or yesterday we have seen type of cutting tool or type of coolant, dry cooling, wet cooling, and minimum quantity lubrication. So these things will come under the discrete or categorical parameters. Now I am going to make these categorical parameters as 0. Okay, but the minimum number of experimental factors or numerical factors selected in the box Bunsen design is 3. Okay, so I am going to give it as 3. So here I can change the values. Cutting speed, I can provide the units, meter per minute. I have to provide only the lower values and the higher values. The lower value, but in the case of Taguchi, I have to provide the level values. I have to provide the level values. But here I am going to give 100 and 300. In the case of the second, it is the feed rate. Millimeter per revolution, it may be 0.5 to 0.9. Then this is the depth of cut, mm. It is 0.15 to 0.45. So the total number of runs here is 17. The total number of runs here is 17. So the central points per block is 5. If I am going to reduce this, I can end up with 12 runs. I can end up with 12 runs, but don't change this. This is a standard design. If I want, I can increase or decrease. If I want to 20 runs, then I can increase. If I want 18 runs, then I can also increase. But in your manuscript, you have to specify the number of center points per block is taken as 6. Is taken as 6, that you have to specify. So now I will go with the standard one. Next comes the response. How many response we are going to have? We can have the previous response itself, ampere, surface roughness in microns, material removal rate in gram per minute. So the experimental design is formulated. In Taguchi, whenever we develop this orthogonal array, the same set of combinations will exist. But in the case of this response surface methodology, because of randomization, each and every time when we develop a new design, it tends to change. So the first thing after developing a experimental design in RSM is to save this. And we have to make a copy of this. Don't forget this. Now I am going to do the experiment. The first experimental run is setting the cutting speed to 300, 0.7, 0.15. So here we can also randomize. Or I can sort it according to the ascending order. This will tend to change. So standard order becomes this. Now, okay. So according to this I am going to do, and then I am going to enter the values. So roughly I will enter now. For 17 values I am going to enter. So I have entered the values. Someone asked, sir, what happens if I forget, if I am going to do that? No problem. You can just save this into a Excel or into a Word file. Then I can easily cut and copy. So cut copy is possible with this. Now on the left side we can see the design, the information, the notes, the summary. In the summary we can have the cutting speed, unit, type, whether it is numerical or categorical. What is the minimum value that I have selected? What is the maximum value that I have selected? What is the mean value, that is the center value? And what is the standard deviation? Similarly for response, I will have, because this is my output that I have provided, what is the minimum value, what is the maximum value, what is the mean value, standard deviations, and all these things. So these are not needed at this now. Okay. So now go with analysis. So first one is the design. So I have designed. Now I am going with the analysis. The next step is the analysis. In the analysis, my output will be listed. My outputs are listed. So first I am going to analyze the flank wear. So I am going to analyze the flank wear. So first we have the transformation. First we have square root, natural logarithmic, base, inverse, everything. But initially don't go with any transformations. If transformation is specifically needed, then go with it. Otherwise don't go for any transformations, and analyze only the raw data. Then I am going for the fit summary. So here we can have whether your model is suited to lower order polynomial or higher order polynomial. Is suited for lower level polynomial or higher level polynomial. For our given readings, the system itself recommends us use linear. And there is a warning here. You can see the warning. The cubic model is aliased. The alias is nothing but the instability between the main effects or the interaction between the selected inputs. So don't go with cubic. So automatically it will take the suggested one. So model. So here you can see the model terms are nothing but the main effects term. Cutting speed, feed rate, and depth of cut. Here you can see M stands for model, and this triangle, or the triangle indicates that there is alias, that is instability with another terms, and these are all lockings. Okay, so I can also change here process order linear or 2f1. If I want to go with a higher order polynomial, I can change here. So the interaction effect I am going to study. If I am going with the quadratic, then I am going with the square terms also. Don't go with ABC because it is aliased. Aliased means there is instability. If the system is presenting you that there is any instability, kindly omit that. So I will initially go with mean or linear. Linear is nothing but the main effects only I am going to select. Now the next tab is the ANOVA tab. Next tab is the ANOVA tab. In the ANOVA tab, we can see the source model. The model of the cutting speed, feed rate, depth of cut. The model is comprised of the main effects only. The model comprises of the main effects only. So the model is not a significant one. That is, the developed model is not significant. There is some problem in this. Since we have taken the reading by our own, there may be some problem. If you have done a perfect experiment and you are going to analyze the data, the model should be significant and it will be significant. If you are perfectly doing your experiment and you are perfectly recording your outputs, and if you want to analyze, then a significant model will be developed. If the model is not significant, then once again I have to run the experiments carefully. I have to record the outputs and then I have to analyze. Here comes the next one, the lack of fit. The lack of fit should always be non-significant. The fit should be significant. The fitting the model should be always significant, but lack of fit, that is, there is some problem in the fit. Okay, lack of fit should always be non-significant. If it is significant, then a perfect model is not possible. It's not possible. How I am going to tell that whether the model is not significant? Kindly look onto the right side. Fit statistics. In the fit statistics, here we come across the regression coefficient terms. Here we come across the regression coefficient terms, R square, adjusted R square, predictor R square. So we are going to do all the statistical analysis considering 95% confidence interval. So a R square value that is nearer to 1 is perfect. But here in this case, it is only 28%. Out of 100%, it is just 28%. So this is not acceptable. So what we are going to do is, we are going to increase the polynomial, low order polynomial to higher order polynomial, and we are going to see whether the model is improving or not. How to do that? Once again, go back to model. Now change it to 2f1, that is a higher order polynomial, and come to ANOVA. Now here you can see in the fit statistics, you can see the R square value tends to increase, but the predicted R square goes in the negative manner. And here in this ANOVA for 2f1 model, in the middle, you can see the model is also non-significant. The model is comprised of A, cutting speed, B, feed rate, C, depth of cut, then the interaction terms also A, B, AC and BC. So the model is not good. So once again I am going back to linear ANOVA. So here minus 0.15. So by increasing the model, the prediction goes worse. Right? Since we have given the values, it is like that. So just this is a training, that's all. Now on the left side, below that fit statistics, we have coefficients in terms of coded factors. In this we have 3 tabs. One is beta coefficients, that is the coefficients, then coded equation, then actual equation. So in these three tabs, go for the actual equation. The model has developed. Here you can see a fitted model. So flank pair y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus minus beta 3 x3. So this is a linear model developed for the lower polynomial equation. If I am going with 2f1, then these terms will also be included in this. In the actual factors, here you can see the flank pair equation now consists of the interaction terms also. The interaction terms also. Now at the top, after ANOVA, I have diagnostic plots. In the diagnostic plot, we can have the normal probability plot, residual plots, and all these things. So this is Decision Expert 11. So here we have combine all tabs. Combine all tabs. Just click that. So each and everything will be displayed individually. So normal probability plot, residual versus run, Cook distance, box cuts, predictor versus actual, and all these things. And finally report. So in the report we can see this is the actual value, this is the actual value, that is my experimental value. By using that actual equation, no, in ANOVA we can see that the actual equation. By using the equations, I am going to predict. And that value is this. So between the difference between these two is the residual. The difference between these two is residual. So here you can see. So for this only we are going to draw this. The normal plot of residuals. So here you can see this has got deviated out. This point. I will just click this point. So standard order 15, run 12. Okay. Now I can go with this design. I am going for run order 12. So run order 12 is this. So there is problem with this experiment. So there is a problem with this experiment. So I have to rerun that experiment because there may be some human error or some vibration exists at that point, particular point. So a wrong reading may be included in our analysis. So normal probability plots, then residuals versus predicted, then residual versus run. So here you can see these things are in between the upper and the lower, and it is evenly scattered out. Then we have the predicted versus actual. So here comes the difference. So a 45-degree straight line is not possible because here you can see it is randomly scattered and a straight line is not fitted perfectly in this. So the values that we have entered for analysis is not good. So the model developed is not good. So from this I can interpret. Then I will go with the model graphs. Here on this ANOVA, diagnostics. Now I am going with model graphs. So this is the contour plot. The contour plot I am going to draw between a cutting speed and feed rate and the output flank pair. So here I can change. On the right side you can see cutting speed x1, B feed rate x2, and C depth of cut. Indeed, right click the depth of cut. You can change it is to x2 axis. Now the depth of cut has taken the x2 axis. Now if I want to feed rate, take this as x1. So similarly like this I can change. So here you can see flank pair is maximum when the feed rate is higher. So in this case, the flank pair is higher with a lower depth of cut and higher and lower cutting speed. So at higher cutting speeds, higher cutting speeds, flank wear is less. So cutting speed has to be improved. So in the top we have the perturbation plot. So with change in A represents cutting speed. Okay, A cutting speed, flank wear reduces. But B feed rate, with increase in feed rate, flank wear tends to shoot up. With the change in cutting depth of cut, the flank wear reduces. Then one factor at a time. So with cutting speed, when the cutting speed increases, flank wear decreases. Now this I can change X1 axis. So feed rate, with change in feed rate, the flank wear increases. Depth of cut, right click, then change the axis. So similarly we can draw it for all the inputs. Then comes the interaction, all factors. So here in one factor, I am going to change the axis. Right click, change the axis. But all these three graphs are seen in all factor graphs. Similarly, here you can see 95% confidence interval bands, because all these statistical analysis are being carried out as per the 95% confidence interval. Then comes the interaction plot. So interaction plot is drawn between two inputs. So cutting speed and then flank wear for feed rate. B is feed rate for flank wear. So this I can change. So what is the interaction effect? Similarly, I can change this also. Then contour plot, this we have seen. Then predictor actual that we have seen earlier. Then comes the 3D surface. So this is the 3D surface. So with the increase in feed rate, a linear increase in flank wear is observed. But similarly, with increase in cutting speed, flank wear tends to increase linearly. But the interaction effect produces lower flank wear. So I will rotate this. So we can also rotate, so that there the lower and upper limits can be determined. So whatever thing I can rotate. So now I can change the axis. Depth of cut, right click, change it to XY axis. So this is like a twisted surface. So I can rotate. So that everything is visible. So with the change in cutting speed, an increase in flank wear is observed, but with the change in depth of cut, this is 0.15 and this is 0.45. With the increase in depth of cut, the flank wear tends to lower in a linear manner. So by using this response plots, we can identify. These response plots are fitted based on the developed model. In this case, in this example, the ANOVA model developed is not significant. So a false interpretation is possible with the model classification. This should be significant. The model should be significant. Since it is non-significant, whatever interpretations that we are going to make in this response surface, perturbations, one factors, contour, everything will be in a based, because a significant model is not developed. So our ultimate aim is to develop a significant model. So here on the right side, now we can see there are three outputs in which I have analyzed the flank wear. So in braces, you can see it is analyzed. The next condition is surface roughness. The next output is surface roughness. So transformation none, then fit summary. Here you can see now the linear has been changed to 2f1. So the system itself is suggesting that we have a very good one. So 2f1 will produce very good results. So here we can also change. We can also see on the right side we have sequential model sum of squares, then model summary, statistics, and all these things. So in this I can see the R square value. We can see the R square value. So here you can see with the linear model only 17%, 0.17 is the R square, but with the 2f1 it is 0.69, but with quadratic it is 0.75. But at the same case we have to look into the predicted values also. The predicted is minus 0.15, but with increase in quadratic it is minus 1.5. So that's why this is not recommended. So this is recommended, but the cubic has 0.90 of R square value, which is nearer to 1. But why it is not suggested? Because it is unstable. Some of the factors, main effects, are unstable with the interaction effects. So it is aliased. So 2f1 I am going with, so model, so 2f1. Whatever suggested it takes. So ANOVA. So here you can see a perfect model is being fitted. So here you can see the model is significant. The model comprises of the 3 inputs and their interaction effects, and the lack of it is non-significant. So this model is a fitted one. This model developed is a fitted one, and the model is a significant model, but with the low R square value. Right. Why the R square value is less? That we can see it from the diagnostic plots. Now here in this right side on the lower window you can see the actual equations for surface roughness. So this is used for prediction purposes. So here in the surface roughness a significant model is produced, and at the same time the lack of it is non-significant. Now I am going with diagnostics. Now I am going to combine all tabs. So here you can see I am moving the cursor here. Now normal probability plot. So a perfect straight line fit is possible because it is normally distributed, but only one point is changed. Okay, that is run number 9. That is run number 9. So go to the design, check the run number 9. This is the run number, this is the run number 9. So do once again this experiment, do once again the experiment and record the outputs, because this is not distributed properly. If this is going to be fitted in a straight line, then obviously the R square value will be improved. Then residual versus run. So here you can see the 9th value, it is out of bound. The 9th value is out of bound. So the 9th value is having higher residual one. So predicted versus actual, the prediction is not possible because what is the value of predicted R square? The predicted R square is -15. That's why prediction is not perfect. The prediction is not perfect. In the report also we can see. So here we can see it is 0.68. The actual value is 0.68, but 0.88 we can see. The third one is 1.70, but we'll have 2.03. Yeah, vast difference is there. So the 9th is our case. So here you can see it is represented in red color. 9. So the actual value is 1.69, but the predicted value is 1.07. So a maximum residual is obtained in that point. So repeat the experiment number 9 and enter the new values and analyze again. Coming on to model graphs. So this is the contour plot. So with higher cutting speed and higher feed rate, the surface roughness is lower. Similarly, depth of cut, right click, change the axis. This also tends to change. So surface roughness is higher for higher cutting speed and depth of cut. But surface roughness should be as minimum as possible. So minimum surface roughness, cutting speed and depth of cut should be as low as possible. So feed rate, right click, change it to x1. So it tends to, so this is a min-max condition. Here you can see it's a min-max condition. So now coming on to 3D surface plot. So this is the surface that I have obtained. So this is the surface. So with the change in cutting speed, surface roughness tends to increase in a linear manner. In feed rate, when the feed rate increases from 0.5 to 0.9, when the feed rate increases from 0.5 to 0.9, surface roughness tends to increase. So this is for x2. So this is a min-max condition. After a maximum, it tends to decrease again. This is also same. With increase in depth of cut, the surface roughness is higher. So with the higher surface roughness, with the higher depth of cut, extreme surface roughness is obtained. Here comes the cube. So cube is drawn between three input parameters and the output. So here you can see the cutting speed, here you can see the cutting speed, then feed rate, depth of cut and the surface roughness values on the edges. So speed varies from A 100 to A 300. And when A is 100, the surface roughness is 1.23928. When the cutting speed is 300, the surface roughness is 1.57. Similarly, we can predict for different values. Now you can see the surface roughness on the left side. You can see the surface roughness is changed to analyzed. Now coming on to the third category, material removal rate. Don't go with any transformations. Fit summary. So no model is suggested here. No model is suggested. Why? We will go with the model summary on the right side. On the right side, in the red plus or minus model summary section, click that. Here you can see the R square value is very, very low. Even though it's rising, the predicted R square value is lower. The predicted R square value is lowering. So it is not suggesting us any model. So it is not suggesting us any model. So model, so you can see the mean only intercept, but change it to linear ANOVA. So it is, the model is non-significant. Here you can see the model is non-significant and the lack of it is significant. Then go with the actual equation on the right side, lower window, actual equations. So you can see it here. So diagnostic. So here you can see a S-shaped curve. This is a S-shaped curve. This S-shaped curve intimates a transformation is required. So initially we have taken no transformations, but in the normal plot of residuals, this shape is like a S, which represents that a transformation may improve the fit. Then residual is shrunk. So here you can see it is not randomly scattered. It is nearby and a lost deviation is occurring. Here you can see the predicted versus actuals. So the issues comes here. So here also we can see the reports. So how much variation is there? Large variation is possible because of the bad prediction model. And model graphs, perturbations. So here you can see if the change in A is the cutting speed. With the change in cutting speed, MRR tends to reduce. That is, when the cutting speed is increased, MRR gets reduced. With the change in feed rate, with increasing feed rate, higher MRR is obtained. With increasing depth of cut, higher MRR is obtained. So that is my interpretation here. Then I am going with the contour plot. So contour plot here we can see. So higher MRR is obtained here in this point. That is for lower cutting speed and higher feed rate. With the higher cutting speed and the lower feed rate, this is my point. So we can click what is the point here. So that is possible. Then 3D surface. So it is very linear. So with increase in cutting speed, MRR tends to reduce. With the increasing feed rate, MRR tends to increase. Now depth of cut, I am going to right click, change it to X2. So depth of cut also same condition. With the change in higher depth of cut values, MRR tends to increase. Then the cube also I can determine. So here I have analyzed all my 3 inputs. So 3 inputs are being analyzed, and now I am going for the optimization third step. First I have designed, the experiment is designed, then experiment was carried out, the outputs were entered, then we have analyzed the outputs, and now we are entering into the optimization procedure. Numerical. Here you can see the cutting speed, goal. What is my goal? Cutting speed, feed rate and depth of cut are my inputs. So it should be in range. So feed rate should also be in range and depth of cut should also be in range. But flank wear, what is my goal? The flank wear should be as minimum as possible. So it is minimization. So my objective is minimization. So here you can see the curve here. So it is the steepest descent. Now surface roughness, goal is minimization, and MRR, the goal is maximization. So here you can see increasing surface roughness in this manner. It's a reverse manner. Now going with solutions. I am going to click the solutions. So I will end up with a report. First I will have this report. If I want a ramp plot, here it is a ramp plot. So lower cutting speed, lower feed rate. The feed rate is 0.55 instead of point. In the yesterday's problem, in Taguchi we have considered 3 levels, 0.5, 0.7, 0.9. And in the 3 values, any one of the value will be taken as the optimum condition. But here in between the level values also we can take. So it does 0.55 and the depth of cut has to be higher range. So that the flank wear is 0.06, surface roughness is 0.14. Someone asked, so what happens when the predictor value is out of bound? That is not at all a problem because it predicts based on the fitted model. Our fitted model is not as perfect as possible because it is the values are given as our own. So the perfect model is not good. So the surface roughness predictor is out of bound. So MRR it is 0.04. So here you can see the disability value is 0.868. So that's good only because with here we are going for multiple objectives. On the top we can see out the bar graph. So this is 0.9257, then 1, then 0.70. So put the average for these 3 things, then I will end up with 0.86. So this is the multi-objective optimization in response surface methodology and that too in box bundle. Now after determining these optimal conditions, now we are going with post analysis. The post analysis will go with point prediction. So here we can enter what is my current current setting, and that we can also study. So the predicted value is this standard deviation, how much it is, that we can do. So this is my optimum in the confirmation. This is my optimum conditions. So in the confirmation experiment, we can enter the observed values and we can have a comparison of these two things. So this is all about the box-Benham design. The box-Benham design, in the information I will go. The design. So I given the lower and upper values, 100 and 300 only I given, but the box-Benham, it automatically takes the middle value as the another level value. So 100, 300, so 200 is the middle value. Similarly, 0.5, 0.9 in feed rate, it has taken 0.7 as the middle value. But in the case of central composite design, it will not be so. We have to change it according to the alpha value, that is the rotatability. Hope you are now well versed with the box-Benham design. So I will just cut this one and I will go with the central composite design. So design experts 11 I have opened. File, new design. So in that new design, go with response surface. In the response surface, randomized. The first one is the central composite. Just click the central composite. In box-Benham design, the lowest or the minimum number of numerical factors that we can analyze is 3. But in the case of central composite design, the minimum number of numerical factors that we can analyze is 2. So here I am going to take it as 3. I don't take any categorical parameters, that I will tell you in the later on session. So 3. Now cutting speed, meter per minute, 100, 300. So here you can see the alpha values. The alpha value I doesn't know now. Okay. Here at the bottom options, you can see that options no. On left side to that options, we can see alpha is 1.68. Just keep as it is. We'll change at the last. So it takes the lower limit as 31.8 and the upper limit as 36.368.18. Now feed rate, millimeter per revolution, 0.5, 0.9. Then the top cut, millimeter, 0.15, 0.45. Right. Now based on the alpha values, these are being selected. But I want only the low value as 100. Because the machine setting is not possible for 31. Maybe the machine setting may not be possible, and also if in some cases negative values will also come. So in that cases that is not at all possible. So how to change this? Go with options. Here you can see options. Here you can see replicates of factorial points 1. Replicates of axial star point 1. Don't change these two things because this is the minimum one. This is the minimum one. The center point is 6. Center point is 6. If I want to increase that, I can increase. If I increase this, these 20 runs will get increased. So it will get increased out. So this is 6. So this is 6. Now here we can have the alpha value. the alpha value is rotatable. The alpha value is rotatable. That's why it is taken at 1.68. That is, in the design space, in order to search for the optimum condition, we have to search in all the directions. We have to search in all the directions, and that is the concept of rotatability. In this case, there is one thing, the face center. The face center is 1. Check the face centered as 1. Click. So alpha value is 1. If I'm going to give it as OK, then here you will see that the lower and higher range that I have selected was taken by the system. So that is the face center central composite design. So alpha value is 1, non-center points 14, center point 6. So total run is 20. Next, how many response now? 3 response. Tank wear, surface roughness in millimeter per minute, microns, and the MRR gram per minute. Finish. So this is my design. So for this, I have to perform the experiment, and then I have to record the values here, and then we can analyze as we have done in the box Benham design. Okay, this is one. Right. Now I am going to change the alpha values to some other values, and we are going to see how it changes. In the cutting speed with alpha value is equal to 1, we can see 3 level values: 100, 200 and 300. 100, 200 and 300. That is, 3 level values are possible with this. And also in this case, we can see so 200.7.3. Trial number, run number 14, run number 11, run number 10, run number 15, and run number 1. So totally 6 experiments are repeated. Why there is repetition of experiments? The purpose of repetition of experiments is to reduce the experimental error. So from this itself we can tell the experimental error is lower. When the experimental error is lower, a perfect model can be fit. A perfect model can be fit in that. Right. Now I am not going to analyze this. First I will design. Then finally we will analyze. So file, new design. Whether we are going to use the same factors? Yes. I am not going to save this present one. So here this is. Now in the alpha value 1 I have taken for central composite. With the alpha value 1 I have ended up with 3 level values. If I want to increase the level values, what I have to do? I have to go with the other values, other alpha values 2. Give it as 2. If I am going to give it as 2, then what is my lowest value? My lowest value is 0 and the highest value is 400. So the middle value is 200. So I have given the level values as low as 100 and high as 300, and the middle value as 200 will be automatically taken. So that middle value plus low value is the lowest value. Middle value plus highest value is the plus alpha value. So minus alpha value is calculated by adding the low level value that I have given with the middle level value that the system has calculated. The system has calculated the middle value as 200. So 200, the difference. So the difference is 100. So 100 minus 200 minus 100 is 100. So that difference will be minused from the low value. So 100 minus 100 is 0. Similarly, the difference is added with the higher value. So 300 plus that 100 is equal to 400. Similarly for this, the middle value is 0.7. So the difference is 0.2. So 0.5 minus 0.2 is 0.3 here. 0.9 plus 0.2 is 1.1 here. Now I will go with this. Finish. So here you can see 5 level values. 0 is there. Here you can see 0. Then 100 is there. Then 200 is there. Then 300 is there. Then 400 is also there. So the number of values, the range, the number of values or input level values can also be increased by changing the alpha value. So now how to how to analyze data in central composite design and how to perform a constrained optimization. That also we are going to see it now. So I have an example with me that I am going to select. So based on this, I am going to perform the experiments and I recorded the values here. So the same similar 20 experiments for different cutting speed, feed, depth of cut. I am going to have surface toughness as my output, flank wear as my output, and metal removal rate as output with alpha values as 1. The alpha value as 1. Now I am going to analyze the surface toughness. No transformations, fit summary. So the system itself is providing the quadratic is best for my case. It is suggesting quadratic. So I should know why the system is suggesting quadratic. So on the right side, go with model summary statistics. Here I can see the R square value is 9719, and the predicted R square value is 82. But see that cubic. The cubic is more higher than that of quadratic. The R square value is 0.99, which is nearer to 1, and the predicted R square is also 82.25%. But why it is not selected? Because there is some instability. Between some parameters, so it is not suggested. So the system is suggesting quadratic model. So the quadratic it has taken. So here you can see the alias terms in the orange triangle. So just omit that. So here I am going to consider only quadratic. ANOVA. In the ANOVA, the model is significant. And the lack of it is non-significant. So here I can see on the right side the fit statistics is 0.97 and the predictor R square is 0.82. And here we can see the actual equation here. So that is used for prediction purposes. Now I am going with diagnostic plots. So here you can see only 2 terms are not able to fit, but perfect fit is possible with other terms. Then residual versus run, the 10:1. Here you can see this is run number 1 and this is run number 9. But this is run number 1, and this is run number 9. So this is easily identified. That is, the run number 1 and run number 2 are out of bounds. Even though it is within the bounds, larger residuals are being produced. Then predicted versus actual. So here you can see a perfect 45-degree straight line is possible. So a perfect prediction is possible with 82% of predicted R square value. So predicted here you can see a close prediction is possible between the actual values and the predicted values. Now I will go with the model graphs. So this is the contour plot, so perturbation plots and 3D surface. So now, yes, previously we have seen only linear graphs, not parabolic surfaces of C. But here we can see a parabolic curve. With the change in cutting speed, the surface roughness changes in a parabolic manner. In a parabolic manner. Now I am going to change it to depth of cut. So here you can see a perfect graph. It is a maximum condition. It is a maximum condition. The maximum surface roughness occurs here at this point. At this point, the maximum surface roughness occurs. That is at a cutting speed of 256. So this represents a min-max condition. You see the surface here. The surface tends to increase and then decreases. That is, after which the surface roughness tends to decrease. Here also the min-max condition. So max-min condition. This max, then minimum. So with the change in depth of cut up to 0.45 or 0.5, the surface roughness tends to increase. Afterwards, it tends to decrease. So a max-min condition exists. So here also you can see a curve, non-linear curve. This is not a linear one. This is a non-linear curve. The Q plot. Similarly, now I am going with the flank wear now. Flank wear, transformation, fixed summary. Once again, quadratic is suggested. Why it is suggested? That we are going to look into the model statistics here. R square value 90.88, but cubic is 92. But look at the predictor R square. It is 0.76. Then it becomes minus, and also it is aliased. So I am going with quadratic ANOVA. The model is significant and the lack of it is non-significant. So how to calculate the percentage contribution, which is a very, very important one. The percentage contribution of the model is equal to the sum of square of this model, that is 0.0063 divided by correlation total of 0.0069. So that is the model values. For cutting speed, 0.0008 divided by 0.0069. That is, the individual terms divided by correlation total will provide the percentage contribution of individual terms. So for residual, the residuals are nothing but the lack of fit and error. 0.0006 divided by 0.0069. That is the error percentage. So likewise, we can calculate the percentage contribution. So once again, the diagnostic curves. So here a perfect normal distribution is possible because all the points are along the fitted straight line. Then residual versus run, okay. No analyzing is possible here. Then predicted versus actual. This is a little bit okay because the R square value is what? 0.76. Right? So that is only 75% is possible. Prediction is accurate. So that's why it is little bit scattered out. Now model graphs, you can see 3D surface, we can see. So here this is a min max condition. It is getting minimum and then going maximum. So min max condition is there. That is up to 256, the flank wear tends to decrease. With further increase in cutting speed, the flank wear increases. Whereas a linear relationship exists between the feed rate and flank wear. Then moving on to the third one, metal removal rate. Fit summary. Once again, the quadratic is suggested. We can see why. The R square value is 95 and the predicted R square is 74. With the cubic, it is unstable. Then model, then ANOVA. The model is significant and the lack of it is non-significant with a high R square value and a reasonable predictor. But this can also be improved with perfect experimentation. So the percentage contribution of model is this sum of square 37,243.54 divided by the correlation total of 39,110.32. So the percentage contribution of cutting speed is 25.380.44 divided by correlation total of 39.110.32. Okay. Now the actual equation is here. The actual equation is here. Then diagnostic curves. Okay. A reasonable normal distribution is possible with this. A reasonable normal distribution is possible. So this is well scattered. Then prediction versus actual. This is really good with that 74 percentage itself. It is a good prediction is possible. Then model graphs, 3D surface. We have a non-linear graph, a parabolic graph. This is a min max condition with feed rate a minimum because it is moving towards minimum and then it is going to maximum. But here with the cutting speed it increases in a non-linear parabolic way. In a non-linear parabolic way. So now here I can change so we can study this also. Now coming on to optimization. Here the input should be in range because it should be within the selected lower and upper level value. So it should be in range, whereas the outputs should be varied. So here you can see the goal for surface roughness is minimized, the goal for flank wear is minimized, and the goal for metal removal rate is maximized. Now I am going with solutions. The solution is the cutting speed is 267. That is, a in-between value is obtained as a optimum value. The feed rate is 0.203, that is the lower value, and the depth of cut is in-between value of 0.37. So the surface roughness is 301, and the flank wear is 0.126, and metal removal rate 193, which are all the predicted values. These predicted values are based on the equations developed during the analysis. For the cutting speed of 267, 0.203 and 0.37, when we give this as the input to that equation, the output is predicted by the actual coded equation. Now we can see the bar graphs. Disability. So because of this lowest disability of metal removal rate, the combined disability is lower. The combined disability is lower because it is the average of these three. Surface roughness 0.74, flank wear 0.94 and metal removal rate 0.60. By taking this average, the combined disability is 10. Then the point prediction. So this is the predicted values and all these things. So observations can also be entered in this and then we can analyze. Now in the optimization, here in this case we have considered only minimization and maximization, and it is unconstrained because we have not provided any target values. Now in this I am going to consider the surface roughness previously as minimized. No? Now I am going to take it as a constraint, that is target value. The target value is, for example, 2. The target value is, for example, 2. 2 cannot be given because it is not the minimum one. So somewhat take it as 3. So target value as 3. So here you can see, now it is been fixed as 3. Now the flank wear, it should be minimized. The material removal rate, it should be maximized. Now the solution. So here in the predicted model we can see the 3 is positioned here and the predicted value is 3.01. So the surface roughness model is well developed or well fitted. So for this the disability is 0.82. Previously it was 0.75. Now with the constraint optimization, the disability value has also increased. So this is the difference between the unconstrained and constrained optimization using design expert, that is RSM in design expert. Okay, now I hope you are all very much clear about how to solve a problem in box-Benston method and then in a central composite design, and how to perform a constrained optimization and unconstrained optimization in response surface methodology. And with this I finish this session and I will be back exactly at 2 o'clock so that we can see some of the basics of ANOVA and how to formulate a ANOVA table and how to formulate the ANOVA tables and the basic calculations. Begin that ANOVA with an example. Thank you.